Now let's look at some application problems. And we've talked about all the different formulas that we have. This is something I would definitely put on your cheat sheet. S equals R theta. And if I were doing a cheat sheet, I would probably write down for myself what types of quantities these are. So this is a distance or length, so is the radius. And the other word for this is the arc length, meaning that you're going around the outside of the circle. Another formula that we had was for the area of a sector. That's 1/2 r squared theta. And in every one of these, the angle measure has to be in radians. S equals V times T. This is just a variation of the distance equals rate times time formula. The S is an arc length, which makes it a distance. The V is the linear speed, which makes it a rate, and time is time. Then we also had the angular speed. That's the angle divided by the time. In a way, it's another variation of distance equals rate times time, only we're thinking about how much of an angle we go through per unit time instead of an actual distance. Let's look at this problem. In this one, they're giving us a radius. So I'm going to go ahead and write down that r equals 20 centimeters. Here they're giving us another distance, and it's saying that the wheel rolls through this distance. That means this has to be an arc length. I'm going to write that down as S equals 60 centimeters. And then it's asking how many radians it has turned through. This is an angle measure, which would be theta. We have an R, we have an S, and we're looking for a theta. That means we're going to use this formula. If I put in 60 centimeters for the S and 20 centimeters for the R, when I divide the 60 by the 20, the units, the centimeters, cancel out, and that's going to give me 3 for theta. This is okay that I don't have any units left because my theta from this formula is always going to be in radians, and radians is not actually a unit because this is what happens, it cancels out. So if you end up with something like this that doesn't have any units, that's good if you were supposed to be finding an angle in radians. So it has turned through 3 radians. Now let's look at this problem. In this one we have a satellite that's in a circular orbit around the Earth. I'm just going to draw this as a circle that represents the path of the satellite. And it tells us the satellite is 6,000 miles from the center of the Earth. This is giving us a distance that either has to be a radius or it has to be an arc length. In this case, it's a radius because it's telling us how far from the center it is. The question it's asking is how far it travels while sweeping out an angle of 120 degrees. Let's say the satellite started here and went 120 degrees around. That would put it over here someplace. So if our satellite is here, 6,000 miles from the center of the Earth, the question is how far it has traveled. That's going to be how far it's traveled around the outside of this circle, which is the arc length. Again, because they're asking for a distance, the distance in these problems either has to be an arc length or a radius. We already have a radius, and this is asking how far we're going around the outside of the circle, which means that's going to be the arc length. The formula that involves the arc length and the radius and an angle is S equals R theta. We have our radius, which is 6,000 miles. We have an angle that's in degree measure. We need to convert it to radians for this formula, and I'm just going to do that inside of the formula. I'm using the unit fraction of pi radians over 180 degrees so that my degrees will cancel. What I have here is 6,000 miles times 120 pi over 180. And I'm not writing the radians in here since it doesn't actually count as a unit. The unit I want to end up with is miles, and that's what I'm going to get. Now I can just multiply and divide this on my calculator. I'm just going to round this to the nearest mile, and this gives me 12,566 miles. So the distance that the satellite traveled from here to here was 12,566 miles. For this one, we have a circular field. We've got a radius for the pivot sprinkler, and it's asking how much area the sprinkler covers if it sweeps out an angle of 25 degrees. The only one of these formulas that involves area is this one. So what we have is the radius, that's our R. We've got an angle in degree measure. We're going to have to convert that to radian measure. I would have 25 degrees times pi radians over 180 degrees. I'm just going to put all of that into my formula. So I can take my R squared in here. And still with these, I go ahead and put the units in here. When I square this, it's also going to square the meters. That tells me if I'm getting the right type of units. If I'm looking for area, I want square meters or square whatever type of distance units. And then for my theta, I have 25 times pi over 180. For this one, it didn't say whether it wanted an exact answer or an approximate answer. So I'm using an approximation, and I'm going to round it to the nearest square mile, which gives me 12,566. And this is, meters, sorry, not miles. It's 12,566 square meters. For this one, it's asking for the linear speed. It gives us how many times the drum revolves per minute, and it gives us the radius of the drum. So the linear speed in our formulas is V. Remember that this is a rate. This is telling us about the angle that this would go through, but it's not giving us the angle. We have to think that one revolution is 2 pi radians. We might as well use radians because we have to use radians in our formula anyway. That means that 52 revolutions is going to equal 52 times 2 pi radians. That would give us 104 pi radians for our angle. So this would be theta. We also have a radius for the drum. Well, this is R in inches. The other thing about this is that when it told us about the revolutions, it actually was giving us an angular speed because it says 52 times per minute. So this is just giving us the angle, but we could also talk about the angular speed, which is W. This is theta over T, so this would be 104 pi radians, and this was per minute, so this would be per minute, or you could say divided by 1 minute, depending on how you want to think about it. So now the question is how to get from here to finding the linear speed. If we go back and look at our formulas, we have this one that involves the linear speed, and I like to try and keep this down so that I only have a few formulas and I don't have to worry quite so much about which one goes where. If I look at this formula that has linear speed, if I solve this for the V, that means V is S over T. Well, I don't have an S, but I do have an R and I have a theta. So I could find the S, and then I actually also have a time of 1 minute that's included in here. I could do it directly like that, or I could also use this formula, and in place of my S, I could put R theta. I already have a theta over T because that's my angular speed. Here I could substitute in the 16 inches for the R, and then for the theta over T, I've got that here, so that's 104 pi radians per minute, or I could write this as divided by 1 minute, either way. Now I can just multiply the 16 times the 104 pi and get my answer. I'm going to round this to the nearest inch per minute. That gives me 5,228. The units I have left, if I ignore the radians, would be inches per minute. And that's my linear speed. One more question. This time we have a pulley with a radius of 14.5 centimeters. That's the R. 15 seconds is a time. So let's say T equals 15 seconds. 40 centimeters of belt going around the pulley, going around the outside of the pulley. That means that this is an arc length. And then we're trying to find the angular speed of the pulley in radians per second. angular speed is w. So out of our formulas that we have this one to find the angular speed. So let's write that one down. We have a time, that's the 15 seconds, but we don't have a theta yet. Let's think about how else we could get theta with what we have. We do have an r and an s. And there's a formula that involves r, s, and theta, and that is that s equals r theta. Let's put in the s and the r and then solve for the theta. Our s was 40 centimeters, our r is 14.5 centimeters. So all we have to do is divide the 40 by the 14.5 to get our theta. And our centimeters cancel out, which is good because this is supposed to be in radians. Theta is 40 divided by 14.5. And to get our angular speed, we want to divide that by the time we had, which was 15 seconds. Now for this one, let's use significant digits. Let's say 2 significant digits. So I'm going to round this to 2 decimal places, and that gives me 0.18. In this one, since our angle was actually in radian measure, this is radians, and that means that for this angular speed we have radians per second.